Today we're going to move into Chapter 4, talking about noisy channels and parity checks. So working with Huffman codes and Shannon's noiseless coding theorem, we were assuming that our encoded data, that was happening perfectly without any errors. Now we're going to start to consider the more realistic case of what happens if our encoded data isn't transmitted perfectly. So there's some sort of error in transmission. So we're going to consider an input alphabet and an output alphabet. That input alphabet is being transmitted, possibly with errors, and ending up in the output alphabet. And then let Pij be the probability that we received Yj in the output alphabet, given that Xi was what was actually sent. So we're going to assume the probabilities are independent of what comes before or after, so that these errors don't depend on what happened before. The errors are going to be independent events. So that will make things a lot simpler for working with these probabilities. Notice here that the input and output alphabets don't have to be the same thing. So in some cases, you'll have more possibilities there, and we'll look at an example with that. Alright, so for the simplest example, let's suppose we're transmitting a 0 or 1 and then receiving a 0 or 1, but maybe sometimes we get the wrong one. So here our input alphabet is going to be just 0 and 1, and our output alphabet is going to be the same, 0 or 1. Now suppose that if we send a 0, the probability that we receive a 0 is 0.9, so 0.9% chance, or 0.9 probability that we get the right thing in that situation, and the probability of receiving a 1 is 0.1. And then suppose if we send 1, the probability of receiving 1 is 0.8, so we're assuming in this case that there's a difference here, that errors with 1s are more likely than errors with 0s for whatever reason, and then the probability of receiving a 0 if we send a 1 is 0.2. So now we can write down these probabilities. So the indexing here is going to be a little bit weird because these are by numbered. So in the input alphabet, this would be numbered 1, 2. In the output alphabet, numbered 1, 2. So when we're looking at probability 1, 1, we're looking at the probability that we received a 0 given that we sent a 0. If these indices are really confusing for you, I'm okay with you switching to other things like saying that P00 is the probability that we received 0 given that 0 was sent, or sort of skipping ahead to the channel matrix, which is the next part that we'll talk about. So the probability that we received a 0 given that a 0 was sent, we know that that's 0.9. The probability, so here, the P12, that's going to be the probability that we received a 1 given that a 0 was sent, so that's going to be 0.1. The probability that we received a 0 given that a 1 was sent, that's 0.2. Probability that we received a 1 given that a 1 was sent is 0.8. So now we can organize these probabilities. Oops, I got them switched here. We can organize these probabilities into a matrix, and that's called the channel matrix for this channel that has some errors. So Pij is the entry in the ith row and jth column of the channel matrix. So our channel matrix here, we've got 0.9 and 0.1 in the first row, and in the second row 0.2, 0.8. So now we're going to consider a little more interesting example, which is what we call an erasure channel. So this is where we consider the possibility that instead of the bits getting switched, that maybe one of them gets erased. So our input channel here is the same as before. We're transmitting 0s and 1s, and our output here is then 0, 1, but also the possibility that our bit gets erased entirely. So we're going to denote that with a star. So that star means that the bit was erased. So we received nothing. Suppose if we send 0, the probability of receiving 0 is 0.9. The probability of that bit being erased is 0.1, and the probability of it being mistransmitted or misreceived as a 1 is nothing there. And now suppose if we send a 1, we have the same probabilities there, so the probability that's received correctly is 0.9, and the probability of it being erased is 0.1. Then figuring out our probabilities here, the probability that we receive a 0 given that a 0 was sent is 0.9. The probability that we receive a 1 given that a 0 was sent is 0. The probability that we receive nothing given that a 0 was sent is 0.1. The probability that we receive a 0 given that a 1 was sent is 0. The probability that we receive a 1 given that a 1 was sent, that's 0.9. And the probability that we receive nothing given that a 1 was sent is 0.1. So here the channel matrix is 0.9, 0, and 0.1 in the first row, and in the second row 0, 0.9, 0.1. So usually we're going to be transmitting a whole bunch of digits or binary digits over whatever channel. So let's suppose we're encoding a word in binary, so this might be using a Huffman code. It's in some way that there's no errors for the first step here, so there are no errors here. Then we transmit this through a noisy channel, so here there can be errors. And then we decode it back, or try to decode it back to the original word. So for this decoding, there are going to be no errors, except for if it'll translate the errors in transmission. So like if you transmit word here, given whatever code this is that I just sort of randomly wrote down, and there are a couple of errors here written in red where the wrong digit was received, and then try to decode that back to a word. So let's look at the situation where the probability of receiving the correct digit is 0.9 and the probability of an error here is 0.1, and that's the same for both 1s and 0s. So then the probability that our 16-digit code is transmitted correctly, so that we get the right thing without any errors, would be 0.9 to the 16th, which is about 0.185. So we've got about an 18.5% chance that we get the correct thing that we sent. And this is only with 16 digits. So even with, like, we'd consider, 9/10 is pretty likely that something's received correctly, the chance that we were receiving everything correctly here is really unlikely. So we can see that even, relatively small chance of an error, that becomes much larger once we're transmitting a lot of stuff. So this can be something to be very concerned about. Now let's try raising that probability a little bit and see what happens. So let's say the probability of receiving a 0 is 0.99, and the probability of receiving the correct thing is 0.99, and the probability of there being an error is 0.01. So now the probability that our 16-digit code is transmitted correctly, so now we're doing 0.99 to the 16th, which is about 0.851. So that's still only like 85% chance that our entire code is transmitted correctly. So even with this higher probability, it's still not great. So certainly error detection and error correction are going to be a big problem that we want to deal with, since even with small chances of errors, it's really likely that there will be some error. So that's something that we're definitely going to want to deal with. Also notice here that in this situation where the probability of something being sent correctly is the same regardless of what we're sending. So here the probability of receiving a 0 correctly was 0.99 and the probability of receiving a 1 correctly was also 0.99. This ends up being a binomial distribution, which will be really nice and make things easier for computation. So something to note there for working on problems in the future. So now we're going to introduce our first method for error detection, which is a parity check. So suppose we're transmitting a binary string, like we have been, count the number of ones, and then we're going to just add an extra digit to the string prior to transmission. We're going to add a 0 to the end of it if the number of ones is even, and add a 1 to the end if the number of ones is odd. So let's suppose I'm transmitting the message 0, 0, 1, 0, 1, 0, 1, 1. So to add a parity check there, I'm going to count the number of ones here. So here we've got 4 ones, so that's an even number, so I'm going to add on a 0 to the end for my parity check. Then let's say I transmit that. So when I transmit that over here, let's say we've got a 1-bit error where that 1 was switched to a 0 in transmission. So now the receiver can look at this, look at that last digit there, and say, okay, so in the previous digits there is supposed to be an even number of ones. And now when I count up the number of ones in the previous 8 digits, I see there are 3. So that's an odd number, so that's bad. I can tell that there's been some sort of error in transmission there, although I can't tell where the error is. Now let's look at this next example. If I'm transmitting 1, 0, 1, 1, 1, 0, 0, 1, my parity check counting the number of ones and zeros, here we've got 1, 2, 3, 4, 5. So that means I'm going to append 1 for my parity check and transmit it with that appended digit. So now the receiver, here we can see we're assuming there's a 3-digit error here. The receiver looks at this last digit and says, okay, in the previous digits there have to be an odd number of ones. But now when I count the number of ones there, we've got 4 ones. So that means that there's an error there, and we've detected that error. Now look at the situation where we've got we're transmitting 1, 0, 1, 0, 1, 1, 1, 1. So counting that, we've got 6 ones, so that's an even number, so I'm going to tack a 0 on there and then transmit that. Here we're looking at a situation where we have 2 errors, so 2 digits were switched here. Now if I look at this last digit, see that that's a 0, then I know in the previous digits there should be an even number of ones, so counting those up, there are 6. So from the parity check, that doesn't tell me that there are errors. The parity check makes it seem like it's okay. So here, the parity check misses that error. So that's because the parity check is only checking if we've got things right up to an odd or even number. So when there are an even number of errors, it's not going to catch that because the parity or evenness or oddness of this stays the same with an even number of errors. So parity checks won't detect all errors, and they also don't tell us where the errors are. So knowing that there should be an even number of ones and there turn out to be an odd number of ones, that doesn't tell me which digit was wrong. So this is just sort of the very beginning for how we're going to look at error detection and correction, the most basic example where we can start to detect some errors. All right, so that's it for this pre-lecture video. Make sure you answer those questions online.